In this video, we provide an overview of our work titled Similarity Search in the Blink of an Eye with Compressed Indices. First of all, what is similarity search? It is the process of searching and retrieving the items in a very large collection that are most semantically similar to a query. These semantics are defined in modern systems by extracting embedding vectors with deep learning models. The embedding vectors are stored in the database, creating special indices that allow us to search the database quickly and efficiently when a new query comes. Similarity search matters because it constitutes the backbone of many important established and rising applications such as web search, recommendation systems, genomics, and AI. For example, we are seeing the emerging use of similarity search in modern large language models to provide factual grounding and long-term memory. Graph methods are the state-of-the-art for similarity search. Here, the database indices take the form of a graph whose nodes correspond to the embedding vectors in our database. The graph is surgically traversed during a search as follows. Given a query, we start at an entry point. Then, at each step, we compare the distances between the vectors of its neighboring nodes and the query vector, and we move to the node with the smallest distance. We iterate this process until we cannot improve any further. We have found the nearest neighbor of our query. To retrieve several neighbors, we allow for a restrictive amount of backtracking during the search. This traversal has the benefit of exploring a tiny portion of the vectors in the database. However, it comes with a random memory access pattern that causes hardware prefetchers to suffer and renders caching ineffective. It is important to note that the distance computation itself is very efficient when using AVX instructions. Thus, the workload is dominated by fetching random vectors from memory and is bottlenecked by the memory bandwidth. Existing libraries fail to reach this optimal operating regime. In this work, we started by taking graph-based indices to their natural memory bottleneck regime. We'll go over the key ingredients of this optimization later in the video. With these optimizations, we took the system to its natural memory bound regime. But is this the best performance we can hope for? As mentioned, graph algorithms are great for accessing a small number of vectors, in the order of only 5,000 vectors for datasets with 1 billion vectors. However, since fetching these vectors is still the main bottleneck, we can further accelerate the search by compressing the vectors themselves. To be successful in our setting, a compression technique must compress the vectors, which reduces the effective bandwidth of the algorithm, provide accelerated distance computations when vectors are accessed in a random order, and, obviously, do not introduce distortions that would severely affect the quality of the search. Existing quantization methods provide some of these benefits, but there is no solution that provides them jointly. In this work, we propose a new quantization technique that achieves all of our goals, unlocking a new level of similarity search performance. We now introduce locally adaptive vector quantization, a novel algorithm that accelerates the search while simultaneously reducing the amount of memory occupied by the vectors. The simplicity of LVQ allows to perform distance computation extremely quickly and yet maintaining a small quantization error. LVQ operates as follows. We start by computing the mean vector for the entire dataset. Then, we subtract the mean from each vector and individually scale it using its minimum and maximum values. Finally, we run a standard scalar quantization for each of its values. In the plot, we can see that with other quantization techniques with the same level of simplicity, each quantized value only uses a fraction of the available range. Effectively, this means that we are wasting bits when encoding each value, causing a degradation in the quantization error and in the accuracy of the search. LVQ, on the other side, uses the entire available range, resulting in more accurate search results. Decoding each vector for computing distances is very simple. Using the minimum and maximum, which are stored with a vector, we undo the scalar quantization and form a vector of floating point values that is used to compute the distances. This can be done directly on the fly in CPU registers, avoiding any additional memory lookups. In the plot, we can see that distances with floating point distinct vectors are faster than with LVQ vector for small datasets that fit entirely in cache. This corresponds to the left portion with flat curves. LVQ 4 and 8 respectively use 4 and 8 bits per value. This speed difference is due to the small decoding overhead we just described, which is meaningful at these small scales. However, when the dataset is large enough to reside in main memory, as is our case and we can see in the right portion of the plot, LVQ starts being faster, as the total time is dominated by the time required to fetch the vectors from memory. Finally, we can see that LVQ allows to overcome the bandwidth limitations imposed by traditional vector formats. Without LVQ, we cannot increase the system's throughput beyond 40 threads, as we have already saturated the memory bandwidth. The reduction in bandwidth from LVQ allows to utilize all available 80 threads with increased performance. All in all, LVQ accelerates the search, allows to use all available cores effectively, and uses a small memory footprint to store each vector. Beyond search acceleration, LVQ can be used to build the graph itself instead of the original full precision vectors. In the paper, we show theoretically and empirically that using LVQ for construction produces a graph of equal quality. Additionally, for vectors of higher dimensionality in the upper hundreds, like the ones commonly used in modern AI models, we use a two-level compression technique that achieves more bandwidth reduction. The critical observation is that the residual vectors obtained by subtracting the LVQ vectors from the original full precision vectors are uniformly distributed. This enables to quantize the residual vectors directly with the traditional scalar quantizer. We thus use the first level LVQ vectors and the second level quantized vectors in a two-level compression technique. We first use LVQ vectors for the graph search, but we retrieve more neighbors than we initially wanted. Then we use the second level residuals to re-rank this small set of candidates and yield the final result. This incurs additional memory accesses, but this overhead ends up being negligible compared to the full search. For deep learning embedding vectors, the two-level approach brings significant performance benefits. Bringing graph-based similarity search to its optimal regime required taking a deep look at the different algorithms and their implementations. After an extensive analytical and empirical study, we converged to a set of optimizations that take the workload to its natural regime. First, we noticed that standard graph formats incur too many memory indirections, which slow down the search. Since the maximum out degree of the graph is a hyperparameter of the algorithm, we can encode the graph using a flat format to accelerate the search. A similar observation holds for the style of coding. Dynamic polymorphism also incurs too many indirections, and we replaced it with static polymorphism. Second, an often overlooked feature in large-scale problems is the use of huge pages. This feature streamlines memory accesses by decluttering the bandwidth from the TLB page accesses. This is particularly important in our case with random access pattern, which hits TLB pages hard. In the plot, we can see the noticeable performance benefits of using huge pages. Another important point is that hardware prefetchers struggle with random accesses. Implementations of graph-based similarity search often include specific instructions for fetching vectors ahead of time so that they are in L1 cache when needed. We found that a simple and yet more advanced prefetching strategy is more effective and accelerates the search significantly. We use a custom prefetching scheme with tunable look-ahead parameters to ensure enough data is brought in ahead of demand request while not exhausting the L1 cache capacity. Notice the blue bars in the plot, which correspond to the new strategy and the acceleration they bring. Lastly, LVQ distance computations can be performed using AVX512 instructions with great efficiency. In typical usages, the dimensionality of the vectors is fixed and given ahead of time. We can then safely define it at compile time, giving the compiler more opportunities to unroll critical loops in the distance computation process. We implemented LVQ and our optimized graph-based index in a new high-performance library for similarity search called Scalable Vector Search. SVS achieves state-of-the-art results, beating other highly performant alternatives. In the plot, we show search accuracy on the horizontal axis and search throughput on the vertical axis for a standard dataset with 96 dimensions and 1 billion vectors. Notice the logarithmic scale in the vertical axis that highlights the performance difference. In the right plot, we show normalized throughput and memory at ISO accuracy for different configurations of SVS, which have a maximum out degree of 32, 64, and 126. With only 32 neighbors, SVS already outperforms its competitors while using less memory than any of them. This behavior is accentuated for 64 neighbors, achieving an acceleration of 4 times. For 126 neighbors, we reach a performance improvement of almost 6 times with respect to the second best alternative, HNSW-lib. We also reduce the memory usage by 200 gigabytes. Every solution uses hundreds of gigabytes, which makes our savings significant from a system's cost perspective. The performance results we just showed are not restricted to a single dataset or use case. We have assessed SVS, comparing it with other state-of-the-art alternatives across a wide range of scenarios. Across different scales, spanning from millions to a billion vectors, across different dimensionalities, we have covered different accuracy regimes, retrieving different numbers of neighbors. We have also evaluated both throughput and latency. In every scenario, SVS is a top-performing library, coming ahead of its competitors. We make our research available to the research community by making SVS publicly available. This release contains everything we have covered in the video, including optimized graph indices and LVQ. SVS has production-ready code written in C++, but it can also be accessed through a simple and yet powerful Python API. We have built a comprehensive documentation with tutorials and dedicated sections to help users tune the performance of SVS. This release of SVS also includes software optimizations that allow to extract maximum performance with Intel Xeon processors. You can download Scalable Vector Search today from the provided link. And if you're interested in trying it or in making your own contributions, reach out.